Hello everyone. Once again, welcome to this TYBSc MMP class. In this video lecture, we are starting second chapter of this course, Special Theory of Relativity. Today we are going to discuss Newtonian relativity, Galilean transformation, and invariance of Newton's law under Galilean transformation. Let us start. As per university syllabus, the topics we have to study in this chapter are Newtonian relativity, Galilean transformation equation, Michelson-Morley experiment, postulates of special relativity, Lorentz transformation, kinematic effect of Lorentz transformation such as length contraction, proper time, transformation of velocities, variation of mass with velocity, mass energy relation, and four vectors. First, we will discuss some basics relating this theory. Special theory of relativity is a scientific theory which is concerned with the relationship between space and time. And this theory is proposed by Albert Einstein. Albert Einstein proposed two theories. One is a special relativity which applies to all physical phenomena in the absence of gravity, and another general relativity that explains the laws of gravitation and its relation to other forces in nature. This theory proposed that the law of physics are equally valid in all inertial frame of reference and speed of light is constant for all inertial observers. To understand this theory, we must clear some terms relating this theory. First term is a frame of reference. What is frame of reference? Frame of reference is a coordinate system. In previous chapter, we have already studied this coordinate system. Frame of reference is a coordinate system used to standardize measurements within that frame. To get clear this term, let us see one example. Let this person A standing on this road, then to describe the position and motion, that is whether this is at rest or in motion. To describe its position and motion, consider this coordinate system. Then this coordinate system which describes the position and motion of this person A is a frame of reference of that person. Let us consider this bus is on the same road. This bus is at rest on the same road and a person B sitting in the bus, and there is a box on front seat of this person B. Then this bus is at rest, this person is at rest, and the box is also at rest. Then to describe its position and motion, consider this another coordinate system. Then this is the frame of reference of this bus and the person. Let this is S dash. Then the situation is this person A observes that the person B is at rest, the box is at rest, as well as the bus is at rest. While the person B observes that the person A is also at rest. Means with reference to this S frame of reference, the S dash frame of reference is at rest, and with reference to this S dash frame of reference, S frame of reference is at rest. Let the bus moves with uniform velocity towards west. Then the person A observes that the bus as well as the person B and the box moves with same velocity towards west. But the person B observes that the person A moving towards east. Person A moving towards east. But the person B observes that the box is at rest. Though the box is moving, but it is in the same frame of reference. Therefore, it observes that the box is at rest. Means with reference to S frame of reference, the S dash frame of reference is moving with uniform velocity towards west, and with reference to s dash frame of reference, the s frame of reference is moving towards east in opposite direction with constant velocity. This is called the relative motion, or this is the relativity. Events are labeled by position and time relative to particular frame of reference. Thus, the events, whatever happening in the frame of reference, are labeled by position and time relative to that particular frame of reference. First topic of this chapter, Newtonian relativity. This Newtonian mechanics deals with motion of objects having velocities very much less than velocity of light. Means in everyday life we see all motions having velocity very less as compared to the velocity of light. Therefore, Newton's laws are applicable to all such motions. The concept of Newtonian relativity. The first concept is all fundamental physics laws and principles are invariant or identical in all inertial frame of reference. Meaning of this, if we perform any experiment in the rest frame of reference or in frame of reference which is moving with uniform velocity, then we get same results. That is, all fundamental laws, physics laws and principles are invariant in all inertial frame of reference. And the second, space, time, mass are all absolute and invariant. These are not affected by motion of object or observer. Space absolute means in its own nature, without regard to anything external, remains always similar and immovable. Space remains always similar and it is immovable, that is not changing. And the time absolute means time exists independently of any perceiver. Time exists independently of any perceiver. It is not affected by position or motion of the object or observer. Whether the clock which recording time, it is in motion or at rest, or the observer which observes the clock is at rest or motion, there is no change in time. That is, time is absolute. Okay? Space, time, as well as mass. Mass absolute means whether the object is at rest or in motion, its mass does not change. That is, mass is invariant. Then the next topic, Galilean transformation. We have to see the Galilean transformation equations that Newton's law hold in all frames related to one another by Galilean transformation. The definition of transformation equations. The equations which relate the two set of coordinates of event in two frame of reference are called transformation equation. We consider two frame of reference, then the equation relating the coordinates of one frame of reference with another are called transformation equations. And Galilean transformation equation relate the motion observed by two observers in two different inertial frames. These Galilean transformation equations relate the motions observed by two observers in two different inertial frames. For this, let us consider this S frame of reference having XYZ coordinate and O is the origin. Consider this another frame of reference S dash having origin O dash and the coordinate axis X dash, Y dash and Z dash. Then at t is equal to t dash is equal to 0. T is the time recorded by the clock in S frame of reference and t dash is the time recorded by the clock in S dash frame of reference. Then when this O and O dash coincides, then the time is t is equal to t dash. At origin of s and s dash coincide. Then let's consider this s dash moves with uniform velocity v. Let this s dash moves with uniform velocity v away from s along x direction. Along x direction. Then some event occur at t is equal to t dash at point P. Let us consider some event occur at this point P at time t, which is recorded by s frame of reference, and at time t dash, which is recorded by s dash frame of reference. As time is absolute, therefore t is equal to t dash. Then as v is the velocity of this s dash frame of reference, then distance covered by this s dash frame of reference in time t is vt. This distance traveled by s dash in time t equal to vt, because distance is equal to velocity into time. Therefore this distance is vt. The distance covered by this s dash frame of reference in time t is vt, because v is the velocity. Then the coordinates of this point P, coordinates of this point P with reference to s frame of reference are x, y, z and time t. And coordinates of this point P with reference to s dash frame of reference are x dash, y dash, z dash and t dash. These are the coordinates with reference to s frame of reference, and this x dash, y dash, z dash, t dash are the coordinates with s dash frame of reference. Then if we relate these coordinates, then we get transformation equation. Then the transformation equation from s to s dash, from s to s dash are x dash is equal to this x dash, this distance x dash is equal to this distance x minus vt. Distance of the point P from this y-axis is x, and this distance of this s dash frame of reference from s is vt. Therefore x dash is equal to x minus vt. There is no motion along y-axis, therefore y dash is equal to y. There is no motion along z-axis, therefore z dash is equal to z. And as time is absolute, therefore t dash is equal to t. Then these equations, which relates the coordinates of the two frame of reference, are called Galilean transformation equations. Are called Galilean transformation equation. And the reverse transformation, the inverse transformation equations, that x is equal to x dash plus vt, x is equal to x dash plus vt dash, y is equal to y dash, z is equal to z dash, and t is equal to t dash. These are the transformation equation from s dash to s. These are called inverse Galilean transformation. Now let us prove invariance of Newton's law under Galilean transformation. The Galilean transformation equations which we have just seen, x dash is equal to x minus vt, y dash is equal to y, z dash is equal to z, and t dash is equal to t. Then the velocity transformation equations. To derive this velocity transformation equation, let this point P moves some distance. There is the change in position. The change in position components of this point P, dx, dy, dz in time dt as per s frame of reference, and change in position dx dash, dy dash, dz dash in time dt dash as per s dash frame of reference, as per s dash frame of reference. Then this change in position in time dt gives the velocity component. As per s frame of reference, the velocity component ux, uy, uz. Ux is equal to dx by dt, uy is equal to dy by dt, and uz is equal to dz by dt. Ux is equal to dx by dt, uy is equal to dy by dt, uz is equal to dz by dt. And the velocity component as per s dash frame of reference. Ux dash is equal to dx dash by dt dash. Y component is dy dash by dt dash, and z component is dz dash by dt dash. That ux dash is equal to dx dash by dt dash, uy dash is equal to dy dash by dt dash, uz dash is equal to dz dash by dt dash. But as per this Galilean transformation equation, x dash is equal to x minus vt, and t dash is equal to t. Y dash is equal to y, t dash is equal to t, z dash is equal to z, t dash is equal to t. If we differentiate this with respect to t, then we get dx by dt. T is constant, derivative of t with respect to t is 1, therefore dx by dt minus, but dx by dt is ux. Therefore ux dash is equal to ux minus v. This first velocity transformation equation. Ux dash is equal to ux minus v. Uy dash is equal to ui, because dy by dt is ui. Therefore ui dash is equal to ui. Uz dash is equal to uz. This way, this three transformation equation, dx dash by dt dash is equal to dx by dt minus v, that is ux dash is equal to ux minus v, ui dash is equal to ui, and uz dash is equal to uz. These are the velocity transformation equations. Then the acceleration transformation equation. From this velocity transformation equation, obtain acceleration transformation equation. Differentiate this with respect to time again. These three velocity components, differentiate with respect to time. Then first, we differentiate again with respect to t dash, then d square x dash upon dt dash square is equal to d square x upon dt square, because derivative of this v is constant, for its derivative with respect to t is 0. Therefore d square x dash upon dt dash square is equal to d square x upon dt square. That is, there is no change in x component of acceleration. Ax dash is equal to ax. Then d square y, if we differentiate again with respect to t dash, then d square y dash upon dt dash square is equal to y dash is equal to y, t dash is equal to t. Therefore ay dash is equal to ay. This y component is also unchanged. Then d square z dash upon dt dash square is equal to d square z upon dt square, because z dash is equal to z, t dash is equal to t. Therefore z component is also unchanged, that az dash is equal to az. All three components in two frame of reference are same. For acceleration is, that is a dash is equal to a, therefore acceleration is invariant under Galilean transformation. Then to derive forces in two frame of reference, let a particle of mass m is placed at point P. Let particle of mass m is placed at point P. Then the component of force F acting on particle of mass m at P in reference frame SR. This Fx is the x component of the force as per S frame of reference, m into d square x. This is the acceleration, because according to Newton's second law, force is equal to mass into acceleration. And in S frame of reference, the acceleration is d square x upon dt square. Therefore, x component is Fx is equal to m into d square x upon dt square. Y component is m into d square y upon dt square. This is y component of acceleration. Fz is equal to m into d square z upon dt square. These are the components of the force on mass m at point P as per S frame of reference. X is equal to m into d square x upon dt square. Fy is equal to m into d square y upon dt square. Fz is equal to m into d square z upon dt square. Similarly, in frame of reference S dash, the components are fx dash is equal to m into d square x dash upon dt dash square. This is the acceleration, x component of acceleration as per S dash frame of reference. Fy dash is equal to m into d square y dash upon dt dash square. This is the y component of acceleration as per s dash frame of reference, and fz dash is equal to m into d square z dash upon dt dash square. This is z component of acceleration as per s dash frame of reference. But we have just seen the acceleration is invariant, that is d square x upon dt square is equal to d square x dash upon dt dash square. D square y upon dt square is equal to d square y dash upon dt dash square, and d square z upon dt square is equal to d square z dash upon dt dash square. And mass m is invariant, absolute. Mass m is absolute. Therefore, the form of equation, that is the force remains same in two frame of reference. The form of equation represents Newton's law of motion has not changed under Galilean transformation. That form remains same. Form of the Newton's law remains same in two frame of reference. One is at rest and another is in motion. The form of equation representing Newton's law of motion has not changed under Galilean transformation. Hence, Newton's law is invariant Galilean transformation. There is no effect of uniform motion on the Newton's law. That's all. Thank you.